Welcome to Lesson 4A, Vapor Explosions.
We're going to have two modules on explosions. The first one will be vapor explosions, and then we'll also talk about particle explosions when you have dust in the air. So let's talk about vapor explosions first. We're talking about a situation where we have some kind of a container, a tank, or a room, and you have some flammable gas inside mixed with air, so it has a certain concentration. For example, think about methane, natural gas, propane, something like that. So let's just call it methane. Suppose we have some mole fraction of methane plus air. There may be other things in there, but just to make it simple, suppose that's all there is. Well, there's something called an LEL, which is the lower explosion limit. It's the smallest concentration at which a spark, so you'll need a spark here. There's also something called auto ignition that happens sometimes without a spark, but we're talking about gases that need a spark, at which a spark will cause an explosion. So your methane sitting there and you have a spark. Static electricity can do it sometimes, so it doesn't have to be an actual spark or like a fire, lighting a match or something. It could be static electricity. And so what happens is if there's not enough methane, you can imagine the situation, there's a very small 1 ppm or something of methane, it's not going to explode. There's not enough methane. If you keep raising the concentration of methane, you'll get to a point where it will explode with a spark. And that is called the lower explosion limit, LEL. Most insurance companies, by the way, require that you be below 10% of LEL. In order to insure some building where they have a gas like this, they would say you better make sure your methane, if it's methane, whatever gas, is below 10% of this LEL. So that's a very conservative estimate. There's also something called a UEL, which is an upper explosion limit, and that you might not have thought about. It's kind of the opposite. It's the largest concentration at which a spark will cause an explosion. So just duplicating what we had, except it's the larger one. It's the upper one. So this is also an important quantity. If the mole concentration is too small, no explosion. And this is the opposite case. If YJ is too large, you also will have no explosion.
Why would that be?
Well, this case would be insufficient fuel, but remember, to burn or explode, you need fuel and oxygen. This case with the upper is insufficient oxygen. You have too much fuel. So again, imagine this tank or room with methane and air. If you have 99.9% methane and just a little bit of air, you have a spark, it's not going to explode either. Inside your propane tank at your gas grill, I don't recommend this, please don't try, but if you somehow could put a spark in the middle of that tank without any opening, it's a sealed tank, it would not explode. Again, don't try this at home. I don't want to be sued for telling you that, but it won't explode because it is above the upper explosion limit. In terms of oxygen, the LEL is sometimes called the fuel lean limit of flammability. People that do combustion also have to deal with this. If you have a concentration of the gas that's lower than the LEL, you're not going to get a flame even, not just an explosion, but even a flame. And the UEL is the opposite, the fuel-rich limit of flammability. Both of these, UEL and LEL, they're dimensionless, but their units are typically percent by volume or ppm, but most appendices and tables I've seen for this do percent by volume rather than ppm. By the way, these are listed on your safety data sheets, as well as something called a flash point. And so that's a third item that we deal with here, a quantity or a property of the gas. This is the flash point. Now this one's different. It's not a percent by volume or a PEL. This is a temperature, and it's a temperature above which there are sufficient vapors to explode. These are always mixed with air. Obviously, if you have a pure substance, it's not going to explode because there's no oxygen. So the flash point units are temperature, either degree C or degree F typically. And so what does that mean? Well, you have a container, and let's look at something that's a little more familiar. Suppose we have gasoline. Everybody knows that gasoline is very explosive.
Cans of gasoline make me nervous.
Suppose this is room temperature and you have some PJ. If this has been sitting there a long time, then PJ will equal the saturation pressure. So you would have a lot of gasoline vapors in there. YJ, remember, was PJ over P or VJ over V. VT, the total volume. So remember that equation from the first week of class. So as long as this PJ over P is greater than the lower explosion limit and obviously less than UEL, that one's not hard to achieve for just a liquid evaporating like this. So what will happen is the liquid evaporates until PJ is equal to PSAT. And if that's greater than the LEL, then a spark would cause an explosion. But if you keep lowering the temperature as T goes down, then PSAT goes down. Remember we showed that table for water. Well, the same holds true for about any liquid. The saturation pressure goes up as temperature goes up, or down as temperature goes down in this case. So imagine this tank of gasoline and you keep making it cooler and cooler, you'll reach a temperature where there's not enough vapors because PSAT kept going down and down, and you're not going to meet this criteria. It turns out that's about negative 50 degrees F, where you won't explode for that case. I'm going to point you to the safety data sheet, sometimes MSDS, Material Safety Data Sheet. For decades, we called it the Material Safety Data Sheet. Now, a lot of websites just call it the Safety Data Sheet. I don't know why they dropped the word material. You know where to find these on the websites. I've shown you this many times, but let's look at a common chemical, benzene. You're familiar with these, the chemical formula. Here's the OSHA PEL, which we've talked about. So the TWA value is the one that we're most concerned with typically. I've talked about that before, 1 ppm. And if you scroll down, you'll find some of these other properties like boiling point, freezing point, vapor pressure. That's an important one that we'll use sometimes. And then here's the three that I just talked about, namely flash point and upper explosive limit and lower explosive limit. What does this mean in terms of ppm? So LEL is 1.2%, which is by volume. That means it's by definition VJ over VT. It's the fraction of volume occupied by that partial volume of the gas. And so that is equal to YJ. So in terms of, just divide by 100 to get it into more proper units, 0.012. And then you multiply by 10 to the 6 to get it into ppm. So this would be 12,000 ppm. So this is the LEL of this chemical in ppm. Similarly, this would be 78,000 ppm. And the flash point is 12 degrees F. What does that mean? Again, if we have benzene in a container and it has vapors, if you get this temperature below 12 degrees, that's F, it will not explode. There just won't be enough vapor, so you'll be below the LEL at that temperature. LEL is a function of temperature. We'll get to that in a minute too, so it's not a constant. These are all at, I'd have to look it up. It's either at 20 degrees or 25 degrees. I can't remember which. We'll just use that as our values when we do calculations. I just wanted to compare also to the PEL. The PEL is 1 ppm, the LEL is 12,000 ppm. So here we see that the LEL is much, orders of magnitude greater than the PEL. And that's pretty typical for these chemicals. So we can make two comments here. If it's bad for your health, you don't want to be breathing. In other words, if it's above the PEL, if the concentration is above the PEL, then it's not necessarily ready to or able to explode. In fact, it's a long shot, very much for this particular chemical. And we can make another statement. If ready to explode, it is most likely, depends on the chemical, but almost all of them are like this, most likely very harmful to your health. You say, well, nobody would be exposed to 12,000 ppm. You don't go inside a tank that has almost, liquid and almost pure benzene in there. You can't even get that high unless you have just a large concentration of benzene, and you would never be breathing that. But in tanks, in ducts, and places like that, it does present itself as a problem. There's a table in the book. I copied it here, table 3.2, the flash point temperatures. These are in degree F, so we have to be careful. And molecular weight, LEL and UEL. We talked about benzene. These agree with what I just showed you. Well, actually, they're a little bit different. Just realized that this is 1.2. This is 1.2%. So these must be at slightly different temperatures. They're pretty close, but they're at different temperatures than that other one. But the flash point is the same, 12 degrees F. We talked about gasoline, negative 50 degrees F, 1.3 and 6.0. So those are similar values to what we had with benzene. The negative 50 means if you're up in the Arctic and it gets below 50 degrees below zero, negative 50 degrees F, which would really be cold, you don't have to worry about your gas can exploding because it won't do it. So that's how these things work. If you have a tank or some kind of a duct or something, how would you avoid these kind of explosions? Suppose you're near that LEL and you want to be more careful, you don't want to have any spark. You can put in ground wires, and the job of that is to prevent sparks. So make sure all your equipment is grounded so that you can avoid some static electricity. You can add humidity. That keeps the sparks down also. And you can replace oxygen with some inert gas, nitrogen, helium, something like that, that would replace the oxygen, replace the air with something like an inert gas. I mentioned temperature. What happens is that LEL goes down with increasing temperature and UEL goes up with increasing temperature. It also turns out the same thing happens with pressure. LEL goes down with pressure going up and UEL goes up with P up. So for either of these, I can plot this as both temperature or pressure. I'm going to just do temperature for simplicity, but if we plot UEL and LEL on the same plot, and suppose you start at 0 degrees C or SATP or somewhere, this is your lowest value on your chart. Suppose you have a LEL that's here and a UEL that's up here. So what happens is LEL decreases with temperature, so it tends to go down something like that. And UEL increases with temperature, it tends to go up something like that. So everything in between here is explosive. So it's above the LEL and below the UEL. Now, what's a problem here, and this is what you'll be calculating on some of the homework and quizzes, so pay attention to this. If we have some YJ, so this is our tank, we have YJ, and maybe suppose this is SATP, it's just sitting there at that temperature and it's not exploding. You could even have sparks and nobody's worried. But if the temperature starts increasing, the YJ stays the same, because if you have a fixed tank with a liquid and the partial pressure might go up with the temperature a little bit, your YJ will go up a little bit. And suppose that the temperature keeps going up, you can reach a point where you'll cross into this explosive area. If you have a tank of pure gas, so all it is a flammable gas with no liquid in it, then YJ is fixed, because it's just the ratio of mole fraction is just NJ over NT, and that is fixed for this case. So this is going to go straight across for that case. And eventually there'll be some temperature at which this will explode. So you have to be careful about that. I'm going to show you some examples. You hear it on the news if you watch the news. There was one actually right around when I taught this lecture back in 2017 when Hurricane Harvey hit. There was a chemical plant explosion, and I remember a couple days leading up to this, everyone said this is going to explode. They had some nasty organic peroxides in there. This is the case that I was talking about before, where you have a liquid stored in a tank and it was below the flash point. And what they did was they had air conditioner units that kept this thing cool enough so that the temperature was below the flash point. But the air conditioners got knocked out by the storm, and everyone said, well, this thing, the temperature's slowly rising, and when it reaches the certain point, it's going to explode. And sure enough, that's what happened. So they knew it was going to happen, and they were explaining some of the chemical bonds and stuff there. But the bottom line is it got a little too hot and it exploded. It was quite an explosion. They were ready for it. So I don't remember that anyone got injured because they had evacuated the area. So that was a case where they knew it would happen. You also see in these old homes, you have leaky pipes, and so the natural gas, which is mostly methane, leaks out and there's a spark. Someone turns a light switch on, that could cause a little spark, some static electricity, someone lights a cigarette, whatever. These houses blow up. I mean, that house is completely gone. This happened in Baltimore just more recently, back in August of 2020. And you'll hear about this when I watch the news. Almost every month or two, you hear about some explosion due to natural gas. Okay, one quick example problem. Benzene vapors are mixed with air in a room. We're concerned about an explosion. So let's calculate the lean fuel to air mass ratio. So we want a mass ratio at its LEL. First of all, you look up on that NIOSH pocket guide, and I already showed you for benzene, and we'll just use the 1.2% at whatever temperature that was. This is LEL, and that's by volume. We want mass, the mass ratio. We also can look up M is 78.1 kilogram per kilomole. And so with that, you divide by 100. So YJ is 0.012 at the lower explosion limit. And this is also equal to VJ over V, as we learned the first week of class. And that is 1.2% by volume. That's what that means. So that's why we can divide by 100 and say that Yj is 0.012. So the fuel to air ratio, which is what we want as mass, Fa is the fuel to air ratio based on mass, is mj of the fuel over m air. And so this is equal to, let's let J equal the fuel, which is benzene here. So Nj over N air, Mj over M air. So remember, mass is N times capital M. So that's a simple equation. And now we have to figure out what Nj over N air is. Now that is not exactly the same as Yj, which is Nj over Nt, not N air. Remember, the mole fraction is the fraction of the benzene over the total, which is benzene plus air. This we just want air. So I'm going to do this two ways. One is an approximate solution, where since the Yj is small, and small is a relative term, 1.2% is borderline small. If you're worried about a couple digits, it's not bad approximation. But since it's small, we're going to approximate that Nj over N air is approximately Nj over N total, which is equal to Yj. So then this becomes F over A is equal to Yj Mj over M air. And so you plug in the numbers 0.012. This is mole of benzene over mole of air as an approximation. And then the molecular weight 78.1 gram of benzene per mole of benzene over 28.97 gram of air per mole of air. And all the units cancel out to give you 0.03235 gram of benzene per gram of air. So the bottom line is F over A is approximately, we only have 2 digits in this guy, so 2 digits is about all we can hope for. So we'll call that 3.2% by mass. You can also say F over A, we already know that number is 1.2% by volume. So that's our approximate answers. These are approximate. How would you do this exactly? Remember, F over A is Mj over not the total, but the air. So this is equal to Nj Mj over N air M air. And what is N air? Well, Y air, our mole fraction of air, is 1 minus Yj if benzene and air are the only two gases in the tank. So remember, I gave you this equation, sigma over J, Yj equals 1. All the mole fractions have to add up to 1, so we can plug that in. So this is equal to Nj over Nt, Mj, and then N air over Nt, M air. And this is what we just talked about. This is Y air, so we know that that's 1 minus Yj. This is Yj, so we can write then our final expression, F over A is Yj Mj over 1 minus Yj M air. Plug in the same values we had up here. And when we do that calculation at the LEL, we get that F over A is equal to 0.03197, which is different from 0.03235. This is the exact answer. But to 2 digits, which is, again, all we're good to here, we would still say F over A is equal to 3.2%. So this is exact. In this case, exact and approximate are the same in terms of significant digits.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.